Okay, so I'm unable to be there again today, but we need to get started on Unit 3. Unit 3 is all about graphing linear relationships. So far in experimental methods, we've looked at designing controlled experiments. So how can we go about setting up our experiment and collecting data in a way that's going to give us high level of confidence in the data that we've collected. And then in the last unit, we really focused on the taking of measurements to make sure that we are being accurate and precise. It can also identify what kind of error we have in our measurements. Well, in this unit, we're going to be focusing really on the analysis piece of our data. So when we go about collecting our data, one of the best ways that we can analyze the results to derive meaning from those results is to create a graph. In the first unit, when we were collecting our data, we were really looking at simply was the independent variable relevant or irrelevant. So for instance, did the mass of the bob have an impact on the period of swing? No, it didn't. That was irrelevant. But we did see in experiment 3 that the length of the pendulum was relevant and did impact the period of swing. Well, that's about all that we can get from just collecting the data and looking at the numbers. So again, in this unit, we're going to get more into the analysis, making graphs, and learning some more about the experiments that we are doing. So your task for today is to follow along with your note packets and get the notes that you should have from the video, and I'll be checking that tomorrow when we get to class. So for the most part, physical sciences does deal with quantitative data. As I'm sure you figured out from the first 2 units, we do spend a lot of time collecting measurements of specific scale. We also are going to design those controlled experiments, organize the data that we collect, and report the data to a wider audience. In this unit, again, we're looking at really how to critically analyze data using graphs. That will also allow us to create a mathematical model, which is ultimately what we want to be able to do so that we are able to make predictions about future events. So if we have a mathematical equation, we can plug in some value that we're interested in and calculate what we would expect to happen if we were to be able to collect those measurements and see what would happen. In the experiments that we've completed so far, we've been able to collect data, analyze data, and draw conclusions. To make these conclusions, you primarily use data organized in a table. However, just looking at data in tables does have some shortcomings. First of all, it's difficult to tell what relationship exists between the two variables in a data table. Okay, I mean, we can tell that if, say, the independent variable is increasing, the dependent variable is increasing or decreasing. But just because, they're both increasing or they're inverse of each other doesn't tell the whole story. How quickly it's increasing or decreasing, whether that change is constant or linear, or if it's some sort of exponential relationship, these are all things that we can only tell by looking at a graph. Secondly, it's impractical to find an equation to allow us to make predictions using a data table alone. So to compensate for these shortcomings, scientists create graphs. The most important purposes of a graph include quick and efficient organization of large amounts of data, demonstration of the relationships between the independent and dependent variables, and again, that calculation of a mathematical equation that fully describes the relationship. So as a couple of examples, going back to the early part of the 1600s, Galileo did his famous experiment with falling objects. He went to the Leaning Tower of Pisa, dropped 2 different massed objects off the top of the Leaning Tower of Pisa, and proved that gravity was gravity was accelerating them towards the ground, and they both hit the ground at the same time. Prior to that test, it was believed that heavier objects fall faster than lighter objects. Well, once he showed that they would both hit the ground at the same time, the next piece of that puzzle was to figure out what the rate was that they were falling towards the ground. And so he came up with this extremely clever device, which we see over here on the left. This is a ramp, and because there was no good timing mechanisms in the early part of the 1600s, he designed this ramp, and down the ramp are these little bells. And so he could adjust the angle of the ramp, put a ball on the ramp and roll it down, and he would adjust the placement of these bells until he got a consistent ring. Instead of, if he just had them equally spaced, you would hear the bells ring progressively faster. He could adjust them, and based on their spacing, he could calculate the rate of acceleration of the ball down the ramp. And so we can see some data that he would have gotten. So for the angle of the ramp versus the acceleration, and we can see that they do increase together. And so what he would be looking for this gravity experiment is what would be the acceleration when the angle of the ramp got to 90 degrees. And so this is the testing that he did to prove gravitational acceleration, and he found that regardless of the sphere that he rolled down the ramp, that when the ramp would mathematically be 90 degrees to the ground, meaning that the ball would just be in free fall, that the acceleration of all objects was 9.8 meters per second squared. So he was only able to get this relationship by collecting data and creating a graph and using the graph to extrapolate that response. Likewise, in the 1800s, a scientist by the name of Schwab gathered sunspot data. And so we can see his sunspot data down here. After plotting the data of sunspots versus years, he was able to conclude that sunspot maximums occur every 10 years. This 10-year sunspot cycle seems to affect our weather, but the direct cause is still a mystery. But as you can see by plotting the data, you can actually see that there is a cyclical nature to the number of sunspots over the years. And so it starts to increase, and then it drops, and then it increases again, and then it drops. And so by collecting this data over the course of about 20 years, he was able to note that, again, sunspots happen, or peaks of sunspots happen at varying intervals. Now, when we go to make a graph, there are some consistent things that we do so that our graphs show the same type of results each time, kind of like in our labs. When we do the labs, we always have our independent and dependent variables. When we put those variables into our data table, they're structured so that the independent variable shows up first, and then all of our measurements of the dependent variable come next. Well, when we set up a graph, we have kind of the same thing. There's kind of this formatting that we always use. So in any graph, there are at least two axes. Some graphs have more than two axes, but we'll be focused on two axes graphs. One axis is the vertical axis, which is called the y-axis. And so as we can see over here from our setup, that y-axis is where the dependent variable always gets plotted. And then we have our other axis, which is the x-axis. And the x-axis is always where we plot the independent variable. So we're always looking for the independent variable change compared to the dependent variable change, so x and y, and we always set things up this way. Okay. So in graphing, the data dependent variable is always graphed that way, independent variable is always graphed on the x-axis. One exception that sometimes gets made is that if we are measuring time, even if time is the dependent variable, we tend to always put time on the x-axis, because in doing so, and we'll get to this when we talk about calculation of slope, that means that we'll end up with a rate. And in science, we love calculating rates, how things are changing over time. And so in order to get that from a graph, time always has to be on the x-axis. Each point on the graph consists of a data pair. One piece of data will refer to the dependent variable and the other to the independent variable. And so we have our measurements of the independent variable. So such as when we did our previous experiments, maybe we did the arc length, or excuse me, the arc size from experiment 1. We would put down what we measured for that, and then we would plot going up the period, and then we would get our point on our graph. In this manner, you're able to determine the relationship between two variables. And so here's another example. So we've got our independent variable down on the x-axis here, and the independent variable for this axis is time in years. So that's down here. Another thing that we should always have on our graphs is have everything labeled. And so this graph, for whatever reason, doesn't have the labeling on it. So we got time in years here. And then on the y-axis, we have sales in dollar amount. Okay, so put that right there. So a door-to-door salesman tracked the amount of sales in dollars he made during each year that he worked as a salesman. This data was then plotted in the graph at the right. So over the course of about 10 years, the salesman kept a record of how much he sold and then put it into a graph. The sales in dollars was the dependent variable, hence why it's on the y-axis, and then plotted on that axis. The years was the independent variable and plotted on the x. So the graph shows that each year the man worked as a salesman, he grew his business and made more money. Now with some additional skills that we are going to acquire, we could and will eventually be able to write a line equation to show how much, depending on the years, how much money this individual would make in the years 2011 and beyond. Okay. Now, if you notice in that graph, I'll go back here for a second. If you notice in that graph, there's a line that goes through the middle of the data. And that's what we're referencing here on this next slide. Best fit lines and best fit curves. So far, most of the data that we have graphed has been linear, meaning that the data points form a straight line. Usually data points form a pattern that will indicate whether or not the data is linear. We're going to be focused solely on linear relationships in this class, but we will talk about some things that are not linear. In future experiments, you'll be asked to draw what is called a best fit line or a line of best fit. All measured data contains some random error. So if you look at the data here, not all of the data lines up directly on that line, and that's because in sales it's not wholly consistent, and so we do have some random error in the measurements here, just like we have in all of our other experiments. Since random error causes some data points to be greater than the actual value while others are less, the best fit line should be drawn such that about half the data points are above and half the data points are below. Now, this is something that we're not going to have to deal with as much ourselves because we're not going to be hand drawing any of our data. We're going to be using computer programs to create our graphs. But when you look at your future computer graphs, you should notice that this is the case, that data rarely ever falls exactly on the line, and that's because of random error. Okay. The best fit line should approximate a linear trend in the data, meaning the line should pass between the data points, and so it's very common, such as it is on this graph. We do have a few points that line up directly on the line, but for the most part, because of random error, they do not. And that's always going to be the case, because as we know from talking about our measurements, random error is always going to be a part of our experiments. Now, although the best fit line might not pass through any of the data points, all the data points should be relatively close. And if there are data points that are far from the best fit line, these points probably contain an unacceptable amount of error and should be checked thoroughly for accuracy. So when we were going through our previous unit, we were talking about precision versus accuracy. We probably aren't going to see a lot of this in our data because we know from taking independent measurements, having everybody in our group take their own measurements, write it down, record, and discuss, if we have anything that seems to be out of line with the other data that's been collected, we're going to recollect that data. And so we're always going to have, or should always have, a high level of precision. And if we have a high level of precision, then generally the accuracy should be good as well. And so we probably aren't going to have to worry about that as much. If it does happen, then we are going to have to deal with it. Now, to find the best fit line, you can use a straight edge. But like I said, we're going to use computer programs, specifically graphical analysis. This is the computer program that we used in physical science. And so you should still have that on your Chromebooks, and that's what we're going to be using to be making all of our graphs. Now, not all graphs produce linear data. Some are going to produce curves such as the one seen at the right here. And so best fit curves are similar to best fit lines in that they approximate the trend in a set of data. The difference, though, is that a best fit line is used when data forms a straight line, and best fit curves are used when the data forms a curve. Best fit curves should still pass between the data points, and while most remaining smooth curves without sharp points or sudden changes in direction. So like what we see here, this would be what we call an inverse relationship. As our independent variable is getting larger, the dependent variable is getting smaller. But it's not happening at a consistent rate. If it was happening at a consistent rate, then we would see a linear line going straight down like this. So we do get these types of relationships in the sciences. Not everything is linear, but we do get this. So that's all I wanted to cover for today. Make sure that you get those notes down. I'll be checking those notes when I return tomorrow, and then we will pick up there talking about different types of linear relationships.